Am I on it?
You're on.
Yeah.
Everybody say hi, new Jenny. Okay. Quadratic functions. First of all, what is the definition of a polynomial? Okay, so here's a fancy definition of a polynomial function. Notice, we are trying to generalize the definition of a polynomial, and you will not see any numbers in this. The more abstract algebra gets, the less numbers become involved. Well, those are subscripts, a little bit different. The a sub 2 is the variable. Okay? So a little bit to remember here about functions. We've got what is a function, what is the degree of a function, what is a polynomial. Okay? If I just want to describe a polynomial that we know nothing about, we don't know how many terms it is, so we use this whole concept of a dot, dot, dot. What are those called, by the way? Ellipses. What do you call it? Yeah, it's a small little scatter plot. Yeah, a little scatter plot in the middle of our polynomial. This is proof as to why you pay attention and not do your homework. Okay. Everybody will get to hear that later. It was wonderful. All right. Nobody knows that it was you, Molly, that said that.
Okay.
All right. So we don't know how many terms there are. So in this particular example, the letter n not only represents how many terms there are, but it also represents the actual value of the exponent. Now, don't be confused. Does a polynomial that has 7 as its largest exponent have to have 7 terms? Or actually, n does kind of represent how many terms there are, but if you include this constant term, there's actually how many terms in this general polynomial? N plus 1. N plus 1 is how many terms this polynomial could have. So a degree 7, now does everybody remember what the degree of a polynomial is? It is the largest exponent, the largest power of the variable. So a degree 7 could have at most how many terms? 8. Okay? This one has how many? 2, we call that a binomial, right? Or you can just call it a 2-term polynomial. I don't care. Okay? Technically, could I write that polynomial so that we see all 8 of its terms? Yeah, but what are the coefficients of most of the terms going to be? 0. Right? There's all 8 terms of this degree 7 polynomial. So coefficients are totally allowed to be 0, right? Any of them? No, your first coefficient can't be 0 because it would be a degree 7 polynomial then, right? So that's why you see up here, a sub n could not equal 0 because it wouldn't be a degree n polynomial. Okay? So these are called subscripts. Why do you suppose they chose to go with the letter A with subscripts rather than a different letter for each coefficient? Well, do we know how many terms this degree n polynomial has? No. What if it's more than 26? We run out of letters, right? So typically, we pick one letter and we use subscripts like this whenever we have some unknown number of terms like n. Okay? So I like these definitions. That's what a generic degree n polynomial function would look like. Cool? Now we are going to primarily today focus on a specific type of polynomial function. What type do you think we're going to focus on? Quadratic, which is a degree 2. 4. It is confusing. You have that prefix quad and so on. You know. So I understand why you would call it degree 4, especially if you hadn't had algebra 2. Hey, quadratic are degree 2 polynomials A can't be 0. If A is 0, it is not a quadratic. Okay? But B and C could totally be 0. Now, who remembers from Algebra 2, what do we call a quadratic function that looks like this? What form is it in? Yeah, in Algebra 2 you called that standard form. Okay, standard form has its nice uses. It's really easy to add two quadratics together if they're in standard form. It's pretty easy to multiply them if they're in standard form. Divide them. I can look at it and easily tell you what the y-intercept is. Y-intercept is what? C. But it's hard to determine what the vertex is, right? You can't just look at it and tell me what the vertex is. It's hard to tell what the x-intercepts are. You have to do a lot of math, like either factoring or the quadratic formula. So it's got some benefits, but it's also not so nice in other regards. What was another nicer form? Well, slope-intercept is specific to line. Vertex form. Okay? Well, watch this. Your book shows the vertex form. Everyone remembers it looks like this, right? And look what your book calls it. What? That's stupid, because there are other two books called the other one, standard form, and so frustrating. I probably will call the other form, the one we just saw, standard form, kind of like our Algebra 2 books do, and I'll call this vertex form. So just make sure you understand the book calls them different things. I don't know, does it really have a name for it? I've heard it referred to as the general form. Yeah. Okay, so we've got this function, f of x equals a, x minus h squared plus k, where again, a is not allowed to equal 0, so on. Now, in Algebra 2, you learned how to graph functions by first just learning how to perfectly graph its parent, right? Everything was in families. All the quadratics were a family, where as long as you could graph the parent, and you knew how to stretch, shift, and reflect things, you could graph any quadratic, right? Is that correct? That's how we graph it. That's the best way to graph to me, thinking in terms of transformations. And so that's going to be how we graph in this class as well. So before we actually talk specifically about graphing parabolas, let's just review how you stretch, shift, and reflect any type of function. Agreed? So let's say we have a family of functions whose parent is the graph y equals f of x. So I'm generalizing. F of x could be anything: radical, quadratic, linear, inverse, sine, cosine, tangent, exponential, logarithm. Okay? These rules apply to any type of function. So we're just going to call it f of x. It could represent anything. Okay? Then, all of the members of that parent's family will be graphs that look like this. Okay? Some number times f of some number times x plus some number, and then all of that plus some other number. So a, b, h, and k would be numbers. And you might see sometimes some teachers don't use h and k, they just use a, b, c, and d, it doesn't matter. Okay? So we need to remember, how does this work? What happens? Now, how do you typically determine the difference between a horizontal stretch or shift versus a vertical stretch or shift?
A horizontal stretch or shift is going to have a coefficient that is less than 1. So it's going to be a graph. And a vertical stretch is going to have a number greater.
I can have a vertical stretch with a number less than 1. We call it vertical squash.
Oh, well,
I can also have a horizontal stretch.
What do you mean by?
Well, I want to know, how do you tell the difference between a horizontal and a vertical?
Oh.
Not the difference between a stretch and a squash.
Okay.
So who knows? For example, if if you're trying to graph y equals x minus 3 squared plus 5, most of you will look at that minus 3 and say, take your parabola and shift it to the right 3. Take it and shift it. How did you know this one was to the right, a horizontal shift, versus this one, which was up, a vertical shift? That's exactly the words I was hoping to hear. Words like outside and inside, right? That's typically what we do. We look at this and we see where the numbers are. Are these numbers inside the parentheses or are these outside? Well, did I change the polynomial at all by adding those parentheses? Now that 5 is inside, does that make it horizontal? Really, it has nothing to do with where the numbers are, but it actually has to do with when. It's a timeline. It's not a location. It all has to do with PEMDAS, order of operations. If you were to plug a number in for x and actually evaluate this thing, which operation do you do first? The subtraction, the exponent, or the addition? The subtraction goes first. What comes second? The exponent, and what comes third? The addition. Which of those operations is the operation that makes this a quadratic? It is the exponent. That exponent is what makes this thing a quadratic. It is its identity. That exponent is the f, right? That is the function. Anything that happens before it in our timeline of order of operations will affect the graph how? Horizontally. Anything that happens in the order of operations before the function affects the graph horizontally. Then, after the function is evaluated, anything that happens affects the graph vertically. So it's not a where, it's not inside parentheses and outside, it's when in PEMDAS. Yes?
So you are not really talking about compressions or stretches, but like shifting.
Oh, in stretches. Like what if I were to say 3 2x squared? That 2 is a horizontal squash, whereas that 3 is a vertical stretch. Now here's the thing, we got to spend a lot of time on this because of all of these operations, which ones did you never see in all of Algebra 2? Horizontal stretches and squashes. So you've never actually seen this before. And there's a reason. Imagine taking a parabola and stretching it horizontally. Couldn't I create the same graph by some sort of vertical squash? Imagine taking a parabola and reflecting it horizontally. Still a parabola, same thing. Every single thing you graphed last year in Algebra 2, there was, instead of horizontally stretching, you could have accomplished the same graph by doing something else, and it's easier. Well, this year we're going to be learning some new graphs where a horizontal stretch is unique. It can't be accomplished by a shift or a stretch like other graphs can. So we will have to learn horizontal stretches this year. Doesn't make sense for parabolas really because, let's be honest, can't this simplify down? What's 2 squared? Aren't these quadratics the same thing? These two? So instead of horizontally squashing by 2 and vertically stretching by 3, isn't it much easier to just take the thing and stretch it by 12? Yes. Okay. So that's why for quadratics you'll never see vertical or horizontal stretches. You'll never see horizontal reflections. But we will start introducing it now, even though it won't show up on the quiz Friday, because stretching a quadratic is silly horizontally. Okay, so let's review all of these. Pick one of those letters, A, B, H, or K. A. What does the value of A do to the graph of this parent function f of x? Stretches it how? Vertically. Now, here's the thing. There's lots of discussion amongst teachers about what's the correct terminology to use. For example, 2x squared versus 1/3 x squared. What does that 2 do to the graph of that parabola? Vertically stretches it by 2. That's great. How would you describe the transformation going on with that one? In my opinion, if you say a vertical squash by 1/3, that is wrong. I would call it a vertical squash by 3. Or a vertical stretch by 1/3, I think is also correct. Okay? You either use the word stretch or squash to describe transformation, or you use the number. And if people see a number less than 1, then they should know what that means. They see a number greater than 1. Does that make sense? So if you say a squash by 1/3, to me a squash by 1/3 is actually stretched by 3. It's kind of like a double negative almost. You're like saying, move that thing to the right, -5. Right? So I will tell it so that's basically our rule. Call this a squash by 3 or a stretch by 1/3. Now some teachers, they do not like you using the word stretch at all when it's not actually a stretch, which I understand. That makes sense, right? Why would you call that a stretch by 1/3 when it's not stretching, it's squashing? So I would encourage you to make sure, well, first, know what your teacher wants. But 2, maybe always play it safe. Use the correct word, but change the number so that it's appropriate. Call it a squash by 3. Does that make sense? I've never seen a textbook that actually standardizes the language. However, IB does standardize the language. And so IB says you would call it a stretch by 1/3 or a squash by 3. You don't call it a squash by 1/3. To me, the word stretch means multiply. The word squash means divide. So you're not dividing by 1/3. You're multiplying by 1/3, a stretch by 1/3, or you're dividing by 3, a squash by 3. Does that make sense? Okay. So either way, what does the letter A do? It is what we call our vertical stretch factor. Stretch, squash, same thing. Okay, A is the vertical stretch factor. What else is it also? What if A is negative? It's a vertical reflection, which how do we describe a vertical reflection? We would typically say a reflection over or through or in. So if I had a -2 x squared, for example, I would say, is that a vertical stretch by 2, then a reflection in the x-axis? Or is that a reflection in the x-axis, then a vertical stretch by 2? Actually doesn't matter. Technically, you should probably go and follow PEMDAS. And PEMDAS would tell you which one of those comes first. Yeah, I don't know. Because technically, according to PEMDAS, you're taking the negative of the 2 first. Then you're multiplying. So technically, according to PEMDAS, they're both happening at the same time. I mean, really, it's a -2 being multiplied by x squared. But is there any difference? Is there any difference between -x squared times 2 and 2x squared negative? Those are going to result in different answers? No. So does it matter if you reflect first, then stretch, or stretch first, then reflect? Doesn't matter. They're both multiplications. Multiplication is commutative, so yes, you're right, it will never matter.
Will there be a case where this will matter?
We'll talk, horizontals get a little bit weird, so we'll see. In general, no, I've never seen a case where it matters whether you reflect or stretch first. Now, a vertical stretch, no. I don't even know. Never. All right, pick another letter. I heard somebody say H. I'll say B for last. Because B is the new one. We don't know what B does, really. Okay, what does H do? Horizontal shift. And how come I wrote it as X minus H and not plus? Because if you see X minus 5, your shift factor is actually positive 5, not negative. X minus 5 shifts in what direction, positive or negative? The positive direction. So it's the opposite of how it looks, right? In order to remember that, I think of a mirror. Imagine you wake up in the morning, you stand in front of the mirror. Okay, so my typical morning, hey, looking good today. Yeah, all right. So when you're looking in a mirror, I thought that was funny. It's embarrassing now. If you don't laugh, it's just awkward. So imagine you're looking at a mirror. If I take my hand and I move my hand up, I perceive the person in front of me moving their hand where? Up. It doesn't look like they're moving their hand down, right? You put your hand up, you see the person in the mirror putting their hands up. But if I put my hand to the right, how do I perceive the person in the mirror? Putting their hand to the left. And when it comes to mirrors, things are backwards horizontally, but not vertically. You know, you don't see a person whose head is down and feet are up, right? But you see left as right and right as left. So horizontal's backwards, vertical's not. All right? Okay. Pick another letter.
K.
K. What is K? It is the vertical stretch. Not stretch, shift. Okay? And it is straightforward. If you see a positive 5, that's shifted up 5 in the positive direction. A negative 3 is shifted in the negative direction 3. And then finally, any guesses as to what B is? It is the horizontal stretch factor. And if it's negative, the reflection over the y-axis. I should say, if negative, what? M. Negative. Okay? Multiplication causes stretches. If you're multiplying by negative, it causes reflection. Addition, subtraction causes shifts. If it happens before the function is evaluated, it's horizontal. If it happens after the function is evaluated, it's vertical. Remember all that? All right, so let's look at some examples, shall we? Really, it shouldn't matter what type of function I give you. You should be able to graph anything. The only thing that should be able to stop you from graphing things is not knowing how to graph the parent, right? In theory. So if I were to say, describe for me the graph of y equals 2 sine of x minus pi plus 3. You shouldn't be able to graph it because you shouldn't know what the graph of sine looks like. But if you did know what the graph of sine looks like, you should be able to tell me how to graph it. So how would you graph it? You start with the graph of sine, and then what are you going to do to the graph of sine? What thing? Stretch by 2? What kind of stretch? Vertical. Beautiful. Vertical stretch by 2. Shift to the right pi.
How can you shift to the right?
For sine, it's actually easier than shifting it to the right 2. Yeah, once we learn how to graph pi. Because sine actually has x-intercept every pi. So seeing something like that is nicer than seeing like sine x. The decimal never ends, but it has a distinct value. Like, I can graph pi on the number line. Yeah, it's like right here. Good.
No, but it never ends. So.
That doesn't mean it's constantly growing. Right? Just because the decimal never ends, 1/3 of the decimal never ends. Does that mean it's forever getting bigger and bigger? Yeah. Some of that stuff's hard to grasp.
There's no pattern.
But it still goes on forever and ever and ever. 3, 3, 3, 3, 3, 3, 3, 3, 3, 3. You know, you can add together an infinite number of things and get a finite answer. It's true. Like, if you were to take, here, let me show you an example. 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32. If I were to continue that pattern forever and actually take all infinity of these fractions and add all infinity of them together, I get the number 2. If you actually add together all infinity of them. So that's an idea, that's a similar idea. It's an infinite sum of fractions, but it doesn't mean the number's huge.
So you keep it, no, there's half and then there's a quarter and there's so never go one.
So everything you're adding on is approaching what? So eventually I'm adding, well, the fractions themselves that I keep adding are getting smaller and smaller and smaller, getting closer and closer to 0. So eventually what I'm adding on doesn't change the number hardly at all. Now here's an interesting one. What if I did 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6? Are those fractions also getting smaller and smaller and smaller, closer and closer to 0? So essentially what I'm adding on is so small it doesn't really do much. Guess what the sum of all infinity of each fraction is? It's actually infinity. Huge. Just keeps growing. Yeah.
Well, then how does the first one?
Because these fractions go to 0 so fast that they don't have any overlap with the sums, and so you don't get carryover. These go to 0 too slowly. So yeah, if I take the sum of the first 6 and I got this weird decimal, well then when I add the 7th on, the decimal parts overlap enough that I constantly am getting carryover and it just keeps making the number bigger and bigger. This is stuff you'll learn in AP Calculus BC, which not a lot of people will take. It's called, this is geometric.
Geometric, oh right.
Yeah.
So you have a coefficient. It's a coefficient.
Yeah. Okay. So, question. Shh, keep listening. So we determined this was a vertical stretch by 2, a shift to the right pi, and a shift up 3. Could I rearrange the order of those transformations in any way and get the same exact graph? Woo.
Yes.
So I could shift to the right pi, then vertically stretch by 2, then shift it up 3. Yeah, I think that would result in the same graph. Could I shift it up 3? Could I shift it up 3, then vertically stretch it by 2, and then shift it to the right pi? No. Right? If you shift it up 3, now all of a sudden you have new y coordinates, that vertical stretch is going to be different. Oh, we're not done. Give this homework a start. This will be a 2-day homework.
99. Good grief.
Every other
99.